Hello, and welcome back to the course on quantum mechanics. We are still on the fourth chapter of this course. So let us review some of the concepts that we have discussed in the previous lessons. So in the previous lesson, we discussed specifically on the quantum spin angular momentum. So the components of the spin angular momentum are not compatible with each other. So they obey these relationships or these commutation relations, but they are compatible with the total angular momentum. And the total angular momentum is also compatible with the Hamiltonian. This is the eigenvalue equation for the total angular momentum, or the square of the total angular momentum. Its eigenvalue is S, depends only on the spin quantum number, S. For the Z component of the angular momentum, these are the eigenfunctions and the eigenvalues. So this is the eigenvalue equation. So its eigenvalues only depends on the magnetic spin quantum number m sub s. And this is a proof that angular momentum is quantized. It's actually a function of, or a multiple of, h bar. So we also discussed about raising and lowering spin operators, wherein their property is just to increase or to raise the value of m or to lower the value of m by 1 unit. So for this course, or for this lesson, we will be talking specifically about spin 1/2 particles. So particles where their s value is, the spin quantum number s is equal to 1/2. So if you have spin 1/2 particles, so their s value is 1/2. This means that their m values will be negative 1/2 and 1/2. Take note, the values of m, the quantum number m, is from negative s to positive s in integer values, or integer steps. So since there are only two values of m, meaning for spin 1/2 particles, they only have two states. So this also implies that if you measure the z component of the spin of the particle, spin angular momentum of the particles, you will only get two values: positive negative 1/2 h bar over 2, negative 1/2 h bar, or positive 1/2 h bar, or plus and minus h bar over 2. So they only have two states: the states sm, so 1/2, negative 1/2, and 1/2 1/2. The state 1/2 1/2 is m is positive 1/2 is what we call the spin up na state. So we now have different main notations for the wave function. The bracket notation, or Dirac notation, this is another notation, up and down notation, and this is the matrix notation. It means 1 0, and that our original wave function, psi plus notation. So for spin down wave function, that is for m, the second state, m is equal to negative 1/2. So this is the shortest notation, just an arrow pointing down. So it's a spin down. In terms of matrix form, it's 0 1. So psi minus. So they sometimes call this the spinor notation. Spinor, spinor notation. So spinors. So the general state of spin 1/2 particles is just a linear combination of the spin up and spin down state. So take note, in this case there are only two states. So if you raise the spin down, you get the spin up. If you lower the spin up, you get the spin down. Only two states. So the general state will be a linear combination of the spin up, psi plus, and the spin down, or psi minus, where c plus and c minus are linear combination coefficients. Now, if you use the matrix forms of psi plus and psi minus, this is 1 0, this is 0 1, and in matrix form this is the general state. So C plus and C minus. So in matrix form this is the general state. It only depends on the linear combination coefficients C plus and C minus. So if you want to get the probability of getting SZ, or if you measure SZ and you want to get the probability that you will get positive h bar over 2 or negative h bar over 2, then you just take the absolute value squared of the linear combination coefficients C plus and C minus. So again, we have already talked about this a lot, that the linear combination coefficients are the probabilities essentially. But this is only true for SZ, if you're trying to measure SZ, because these wave functions, there's these time independent states, are the eigenfunctions or the time independent states for SZ, which happens to be also the time independent states for S squared, since they share the same eigenfunctions. So of course you get a total probability C plus squared and C minus squared to be equal to 1. So this is the normalization condition. Again, the assumption here is your spinors, your wave functions, are normalized. So their absolute value squared is 1. Okay, with regards to this total angular momentum S squared, then for S is equal to 1/2, then its eigenvalue is 3/4 h bar squared. So take note, they share the same spinors, or they share the same eigenfunctions. So we now have many terms for the wave function. You can, if they obey an eigenvalue equation, then you call them an eigen function, an eigenfunction or an eigenspinor in this case, eigenfunction or eigenspinor. So SZ and S squared share the same eigenspinor or eigenfunction. So spin 1/2 operators are actually 2 by 2 matrices. So for the S squared, this is basically 3/4 h bar squared times the identity operator in 2 dimension. So 1 1 0 0. This is the identity operator. So 3/4 h bar squared times the identity operator. For SZ, this is the matrix form of the operator. So it's a 2 by 2 matrix. And this matrix is actually what we call a polyspin matrix for Z, sigma Z. Similarly, for Sx, you get that one, a polyspin matrix for Sx, or for X, and for Y, that one. So these are the spin operators, S squared, SZ, Sx, and Sy. S squared and Sz share the same eigenfunction. Sx and Sy have different eigenfunctions. So the 3 sigma matrices here are called the Pauli spin matrices. So let's now go to an example. So what happens when Sx and Sy acts on the eigenstates of Sz? So the result of this problem will show you that the eigenstates or the eigenfunctions or the eigenspinors of Sz are not the eigenfunctions or eigenstates or eigenfunctions of Sx and Sy. So let's first let Sx act on psi plus spin up the spin up state. So Sx is h bar over 2, 0 1 1 0. So this is the matrix form of Sx. And for psi plus, the spin up, the matrix form is a Coulomb matrix, 1 0. So you get 0 0. So the first element is 0, and then 1 0. So the answer of this is matrix 0 1. Where 0 1 is the spin down na matrix. So Sx acting on spin up will actually give you h bar over 2 spin down. Similar, you do the same for sy, for sx acting on psi minus. So this is just a very easy matrix multiplication. I will leave the rest to you. Okay, so these are the results. So I'm just gonna summarize them. So sx acting on spin up will result in a spin down. In terms of the arrow notation, so sx acting on up will be equal to h bar over 2 down. And sx acting on the spin down, or psi minus, will result in h bar over 2 spin up. Similarly, for sy, it will also basically lower the state. From up, it will change it to down. From down, it will raise it to up. So it will raise or lower the wave function, or the state of the particle. So this implies, take note, these are not eigenvalue equations because you don't get the same state. So therefore, the eigenstates of Sz and S squared, which is psi plus and psi minus, are not the eigenstates for Sx and Sy. Okay, let's go to another example. So if you measure the x component of spin angular momentum, Sx, of a spin 1/2 particle, what values might you get, and what are their probabilities? Okay, so for this case, we will now try to find the eigenvalues for S of Sx and its corresponding eigen functions. So we need to do this. So this is the eigenvalue equation for Sx. So psi plus and minus, we will expect that it will have two eigenvalues similar to Sz, and it will also have two eigenstates, a spin up na state for Sx and a spin down na state for Sx. So we just denote a superscript x to denote that these are now eigenstates of Sx. Okay, so to solve for, this is an eigenvalue equation. Now to solve for the eigenvalues, we use the characteristic equation. I will not be doing this anymore because I think we know this. So this is just the determinant of this matrix subtraction. So the Sx, you already know the matrix form of Sx. This is just some numbers, the eigenvalues, the value. And I is just the identity operator. In this case, the two-dimensional identity operator, or 2 by 2 identity operator, 1, 0, 0, 1. So you take the determinant of the difference of these two matrices, and you will get these eigenvalues. Well, obviously, it should be like this. So it has the same eigenvalues as Sz, positive h bar over 2 and negative h bar over 2. The positive h bar over 2 corresponds to the spin up na state. The negative h bar over 2 corresponds to the spin down na state. Similarly, for Sx, if you solve the eigenvalue equation for Sx, you will notice that it will also have the same eigenvalues, plus and minus h bar over 2. Okay, so knowing the eigenvalues and the states. So since we described the state of the particle, the general state of the particle in terms of the wave functions, the eigenfunctions of Sz and S squared, psi plus and psi minus. So we write the general state as the linear combination of the eigenfunctions of Sz and S squared. And since this is the spin up for Z, this is in matrix form, this is 1, 0, and in matrix form, this is 0, 1. Then in matrix form, the general state is just C plus C minus. I have shown this equation to you earlier. Now, we want to write this general state in terms now of the eigenvalues of, in terms now of the eigenfunctions or eigenspinors of Sx. So, like this. So we need to equate this or write this in terms of the eigenfunctions of Sx. And by doing so, we can solve for the linear combination coefficients for Sx, C plus x and C minus x, and this will give us the probabilities. The probabilities for getting plus h bar over 2 when you measure Sx, or the probability for getting negative h bar over 2 for measuring Sx. So that is the bulk of the problem. Now, we know the eigenvalues. We now try to solve for the eigenfunction. So you already know these steps before. So you first solve for the eigenvalues for, the eigenfunctions for spin up. So for the spin up, the eigenvalue lambda is positive h bar over 2. So since this is unknown, but you know that this is a matrix. We try to solve the matrix form. It has only two components. So we have two unknowns, alpha and beta. So we use the matrix form of Sx. Our unknown eigenfunction is alpha beta, and then solve for alpha and beta. We know that, and we derive that alpha must be equal to beta. So this is just alpha alpha. So we only have one unknown. So alpha alpha. Now, to solve for alpha, we use the normalization condition. With that, we take the inner product of this with itself. So the bra version of this is a row matrix alpha beta multiplied by this, so that you can solve for alpha. And you will get alpha is equal to 1 over square root of 2. So basically, this matrix is 1 over square root of 2, 1 over square root of 2, or if you take out the constant 1 over square root of 2, 1, 1. You do the same for psi minus, and you will get this eigenfunction, 1 over square root of 2, 1, negative 1. Okay, so we now know the eigenfunctions, we now know the eigenvalues. Let us now try to write the general state. So I'm just gonna use my board mode here. So let's now try to write the general state, which is in terms of C plus and C minus, linear combination coefficients for SC. We will try to write this in terms of, okay, this one na lang. So I will not be writing it again and again. That one. So we will equate the general state, which is a C plus C minus. We will equate it to C plus of x. This is still unknown, but the wave functions, we already know this one. So this is 1 over square root of 2, 1, 1. The C minus of x, this is unknown. But the psi minus, the spin down for Sx, is 1, negative 1. Add the two column matrices, and you will get one over square root of 2. First element is C plus x plus C minus x. The second element is C plus x minus C minus x. Okay. So this means that this implies C plus is equal to 1 over square root of 2 C plus x plus C minus x, and the C minus is just minus here. So from this is actually two equations, and we have two unknowns, C plus x and C minus x, so this is solvable. We have many methods in solving two equations to unknown, substitution. So you do that, and you'll find out that C plus x is just equal to C plus C minus over square root of 2, and C minus is C plus minus C minus over square root of 2. So that one. So this is the linear combination coefficient for psi plus, spin up for psi minus, and this will give you the square of this c plus x squared. This will now give you the probability that if you measure Sx, you get the positive eigenvalue, the positive h over 2 eigenvalues. So you will get c plus c minus squared over 2. Similarly, for c minus, the probability is c plus minus c minus squared over 2. So these are the corresponding probabilities for the two eigenvalues, the plus h bar over 2 eigenvalue and the probability for the minus h bar over 2 eigenvalue. So as a summary, we measure the eigenvalues to be plus and minus h bar over 2. And this is now the eigenvalue equation for Sx. So these are the eigenfunctions of Sx, and these are the corresponding probabilities. If you measure Sx, there are only two values, two possible values that you will get, plus and minus h bar over 2, and these are the corresponding probabilities. Of course, if you add the two probabilities for the plus and the minus, you will get 1. The total probability is 1. So if you do the same for Sy, this is the eigenvalue equation for Sy. It will also have the same eigenvalues, plus and minus h bar over 2. So its eigenfunctions have an imaginary part. So plus and minus I. So instead of plus and minus 1 for Sx, plus and minus 1 I for Sy. So for Sz, the eigenvalues are 1, 0, and 0, 1. Spin up and spin down states. And these are the probabilities if you measure Sy. So there are two probabilities here corresponding to the positive h bar over 2 eigenvalue and the negative h bar over 2 eigenvalue. Okay. So example number 3. Suppose a spin 1/2 particle is in the spin state. So this is a spin state. This is not an orbital state. It's a spin angular momentum state. So what are the you can always assume that if the angular momentum is 0. So what are the probabilities of getting plus h bar over 2 and negative h bar over 2 if you measure Sx, Sy, Sg, Sx, and Sy? So we already have the equation in the previous problems. So of course, in this problem, you must write this, your psi, as c plus and c minus. So it's obvious here that c plus is 1 over square root of 6, or 1 plus I over square root of 6. And c minus here is 2 over square root of 6, or 1 over square root of 6 times 2. So therefore, 1 plus I over square root of 6, absolute value of that, square of that. Take note, the meaning of absolute value is conjugate times itself. So if this is your c plus, take the absolute value of this over square root of 6 squared. This means that you will multiply 1, its conjugate, so 1 minus I over square root of 6 times itself, 1 plus I over square root of 6. And you will get, so 1 plus 1 minus I squared is negative 1, so 1 plus 1, so 2 over 6, or 1/3. So that is the result here, 1/3. So for the probability of getting negative h bar over 2, if you measure Sz, is c minus squared. So c minus is just 2 over square root of 6, so you have 4 over 6, or 2/3. So from the formula for x, for probability for Sx, you have this one, and you will get this result for p plus and for p minus. You will notice that the total probability should always be equal to 1. So finally, if you measure Sy, this is the probability. So the probability of getting positive h bar over 2 is 1/6, and for negative h bar over 2, it's 5/6. So the total probability is still 1. Now, what are the average values? So there are only two possible values: positive h bar over 2 and negative h bar over 2. Now, uh, what are the average values? So, for instance, if you measure Sx, the value positive h bar over 2 has a probability of 5 over 6. So, most of the time, you will get positive h bar over 2. And less of the time, you will get the negative eigenvalue, negative h bar over 2. That's what these probabilities mean. So, mas higher, positive h bar over 2 has a higher probability of occurring as compared to negative h bar over 2, which is only a probability of 1/6. Now, if you try to measure it repeatedly and you get the average value, so most of the time you get positive h bar over 2, positive h bar over 2, and then negative h bar over 2, and if you add those all and take the average, what is the average value? So, in this case, there are two ways to solve for the average value. So, again, in quantum mechanics, we call that the expectation values. So, you can either, if you take the average value of a quantity Q, sandwich them between your spin states, or take the summation of their Cn squared, their linear combination coefficient squared, times the Qn are the eigenvalues. So in this case, in our case, our Q's are the Sx, Sy, or Sz, the matrix forms of these three operators. Our spin state is given. That one is our spin state psi. And our Cn's here are the C plus and minus for Sz, C plus and minus for Sx, and the C plus and minus for Sy. And the Qn's here are just two values. They all have the same values, plus and minus h bar over 2. So you can do two equations. I'm just gonna solve one, and I will leave the rest to you. So for example, if I want to take the average Sx, for instance, so if I'm gonna measure Sx, the average value of Sx, I'm gonna use the first formula. So you will have the bra. The bra version is the transpose conjugate of this. So you will get 1 over square root of 6, and it now becomes a bra row matrix. So 1 minus I is the conjugate, and then 2, and then our Q here is Sx. So Sx, the matrix form of Sx is h bar over 2, 0, 1, 1, 0. And then, of course, the psi, our original psi, which is 1 over square root of 6, 1 plus I, and then 2. Okay, we take all of the constants, join all of the constants, that will give you h bar over square root of 6. Square root of 6, you get 6 times 2, so h bar over 12. You get 1 minus I, 2, and the multiplication of these two matrices here. So 0, 2, 2, and then 1 plus I, 0. So 2, 1 plus I. So you multiply this, you have 2 minus 2I over 2 plus 2I, and you will actually get h bar over that one. That is using the inner product formula. Now, you can only use this formula if your physical quantity Q is quantized. It has eigenvalues. So if that is the case, then you can also use the second formula in terms of summation. So in terms of summation, so if I'm going to use that summation, expectation value of Sx will be summation of n. So that's actually just there are actually just two members of this summation, C plus of x squared, which is just the probability. We have solved this one here. It's 5 over 6 qn, which is h bar over. So this is the probability, sorry, the average value if you measure Sx. So this is the first member of the summation, the second member is a C minus. And this is negative h bar over 2, so I measured minus. The minus sign is because the second q and the second eigenvalue is negative h bar. So we already know this. This is just a probability. If you measure Sx, so this is 5, 6. So this is 5, 6, 5 over 6, and this is 1 over 6. You will have 5h bar over 12 minus h bar over 12. So you will get 4h bar over 12, or h bar over 3. So you will still get the same result using the other formula, h bar over 3. The same result, h bar over 3. You do the same for sy and sz, and you will get these results. So for Sx, of course, it's h bar over 3 is the average. This means that most of the time you get a positive value, the positive h bar over 2. Now for Sy, the average value is negative h bar over 3, meaning most of the time you will get the negative h bar over 2 eigenvalue, because it has the higher probability also, 5 over 6, the negative eigenvalue. For Sz, it's also negative, so meaning most of the time you will get the negative eigenvalue, the negative h bar over 2 eigenvalue, as can also be seen in the probability here. Its probability is 2/3 as compared to the probability of getting plus h bar over 2, which is only 1/3. Okay. Okay, for the last example. Okay, so this is like a traditional problem. You are given the state of the particle. You are to determine the normalization constant, find the expectation values, find the uncertainties, and confirm that your results are consistent with the uncertainty principles in angular momentum. Okay, let's first solve this one by one. So find the normalization constant. So finding the normalization constant, you just use the normalization condition. The normalization condition states that psi squared must be equal to 1. So this is just the bra version of this, the inner product of the state with itself. So the bra version of this is a row matrix, A conjugate, so negative 3i 4, and then psi, so there's still an a, so it will become a squared here, and then you will have positive 3i 4. This should be equal to 1. So doing that, you will get a is equal to 1/5. So meaning your psi now is actually 1/5 3i 4. This is now your normalized wave function. Now for letter B, find the expectation values of Sx, Sy, and Sz. So I already showed you the process before. I will no longer repeat that process. So you just take the inner product to solve for Sx, expectation value of Sx again. You take the inner product of the spin states, or you sandwich Sx between your spin states side, which is exactly what we have done in the previous example. So doing that will give you what? So Sx is 0, Sz, Sy is that one, Sz is that one. So it's just matrix multiplication here. It's just very easy. So what does this mean? If the average value is 0, this means that half of the time the values that you will get is positive h bar over 2, and half of the time the values that you will get is negative h bar over 2, such that you will get 0. So you will notice also here that if you try to calculate the probability that if you measure Sx, you will get plus and minus h bar over 2, the two probabilities are the same. And you will get, that is the reason why you get an average of 0. Okay, letter C. Find the uncertainties in the uncertainties sigma Sx, sigma Sy, and sigma Sz. Now, in order to solve this problem, letter C, take note that the sigma x, the standard deviation, sigma, that's actually, if you're trying to measure sigma Sx, that's actually the expectation value of Sx, expectation value of xx squared, s squared, minus the expectation value of Sx squared. That is the how you calculate. So we already know the expectation value of Sx. It's actually 0. But we still don't know the expectation value of Sx squared. So what you will do is just find the matrix form Sx squared first. And then you sandwich it with your given spin states. The same process. But what is Sx squared? So basically, Sx squared is just Sx operated twice. So you will get h bar squared over 4 and then 1, 0, 0, 1. So basically, this is just the identity operator. Similarly, for Sy squared, you will get the same result. So this is actually what happened when you square. When you try to square the Pauli spin matrices, the sigma x, sigma y, and sigma z matrices, you will get, or when you operate twice, they will actually become the identity operator. So basically, the expectation value of Sx squared here, so this is just the identity operator. The identity operator acting on any function will just be that function. So basically, you will have the inner product of psi and psi, which is just 1, because we normalize it. So basically, h bar squared over 4 is the expectation value of Sx squared. And that is also the expectation value of Sy squared and Sz squared. So knowing that, you can now solve for the uncertainties. And you will get these values. Okay. So you will get these 3 uncertainty values. Now, you need to confirm that sigma S x, sigma Sy will be greater than or equal to h bar over 2, the absolute value of the expectation value of Sz. So cyclic, this is cyclic. So I and j and k here can be x, y, and z. So you just multiply sigma Sx and sigma Sy, and you need to prove that their multiplication should be greater than or equal to h bar over 2, the absolute value of the expectation value of Sz. And then for Sy and Sz and Sz and Sx, you also do the same. So this greater than or equal to requirement should not be violated according to the uncertainty principle. Okay. And that is the end of this lesson. So we focused on, in this chapter, we mainly focus on the spin angular momentum, and we focus on the spin 1/2 particles in this lesson. So in the last lesson for this chapter, we will further focus more on the electron, one of the most important spin 1/2 particles, the electron. So in the last lesson for this chapter, we will discuss about the spin 1/2 particle called the electron. So I will see you again in the next lesson.